This is, yes, so what this is happening is because we're using D, and we only know D if we chose, like we're using the private key. Yeah, exactly. So because we're using the private key, not the public key to sign, but then D is also used in the public key. And the public key is known, so essentially we can do the calculation using Q. I see. Okay, the beauty here is that we know these, we know DG, right? And I'm not going to go through the details of these. I can do that in another session probably. That's worth it. But essentially, yes, now I understand. So it's because we're using because we know the public key, and the public key actually is computed using the private key, then there is an operation we can make on that signature that essentially guarantees that you know that we use D. Hence, you know the private key. That's pretty nuts, actually. It's quite cool if you think about these. You compute these two scalars, which is E and the inverse of S. This guy here. Then U2, which is R and the inverse of S. Then you compute a point, which is basically using this linear combination of G, which is the known thing. It's the known point. And then Q. And then check if the x of this point equals R. So essentially, yes, you've put in here a Q which cancels with this D, right? And so you're making it cancel. You don't know what it is, but you're making it cancel. This is pretty nuts. Okay, so I think I'm ready for these. So essentially, we know these because you can make a calculation. Let's remove these. So we know we can verify the transaction because there is a math you can run that essentially cancels out D and cancels out a component that is what exactly you're using to create the private key of that public key. So you can prove it without knowing that number, but you can prove it because you know that it mathematically cancels, and you can prove the equality.